On. Here we go. We begin with a word of prayer. So, Dear Father, we thank you for this day again. I thank you for this class. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. So I am a bit behind, and so I thought I would use the projector for a bit in here and fix. Well, I mean, what we did last time wasn't wrong. It just wasn't very efficient, right? And so, for lack of imagination, I will fall back on the book's arguments, which are good. And they also have more applicability later as well. But so in the course planner, I have like 5.3 and 5.4 under these topics, which is nonsense. It's like 6.3 and 6.4 is what I'm covering. All right, more or less. And so here his starting theorem is if you have a finite dimensional vector space over inner product space over a field, and you have a mapping from the vector space to the field, this is called a linear functional. Then there exists a unique vector y for which alpha x is the inner product of x with y. All right, and so here's the proof of that. If we have beta is an orthonormal, I'm going to turn off half of the lights in here so it's a little bit better to see. So if beta is an orthonormal basis, I can construct y like this, all right? And so I'm given the alpha, so I can take alpha, I can evaluate on the basis, I can conjugate that and build this vector. If I do that, then I can define h by taking the inner product of x with that y. And then basically my claim is that h is going to be alpha. All right. So if we look at h on the basis, vj, that's vj with y by construction, which then, well, that's how we constructed y. All right. Which then, as we proved, we pull out the constants from the second slot, it conjugates it, right? Conjugates the thing again. But we assumed that the basis is orthonormal, so that's the Kronecker delta, which is the natural enemy of this finite sum, leaving us with just the jth term. And so there you have it. H of vj is equal to alpha of vj, which means that these two functions restrict to the basis and they're equal. And they're also linear. So it follows that h is equal to alpha. Now, I would point out here, just talk more about this in a future lecture, not so much today, but in fact, what we're doing is we're trading a linear functional for a particular vector using the inner product. This is actually what's known as the musical morphism. We're taking the sharp of alpha to create y. But I'll say more about this in a later lecture. I mostly talk about musical morphisms in the context of real vector spaces, so I don't really want to say more about it right now because we're going to be pretty complex for the most part today. So, all right, so why is it unique? Well, suppose you had another vector y prime for which alpha x was equal to x y prime for all x, right? Then that would give us that xy is equal to x y prime for all x, but we've proved a cancellation property for the inner product before, right? If we have this is equal to that for all x, well, that implies y is equal to y prime. Therefore, the vector which we've constructed that serves this purpose, right, alpha of x is equal to x with y, that's a unique y. If I pick any other y prime, I get the same y that I just constructed. So I have that uniqueness. That's important because we're going to use this construction to build a function on the next page here. So the next step in this game we're playing is to basically build the adjoint. So theorem 6.9 says, finite dimensional inner product space, T a linear transformation, there exists a unique T star, which is linear on V, for which T of x with y is equal to x with T star y, like that. Now I built that last class using an explicit coordinate calculation, right? And this argument supplants that, all right? You'll see. We'll get back to what I did yesterday in a bit, but here we go. So I have not defined T star at this point. like, you have to erase your memory from last class. We have not yet defined T star, okay? So, all right. If we have a linear mapping from V to V, we can let Y be an element of V, and we can define alpha sub Y of X to be the inner product of T of X with Y. My argument is that this alpha sub Y defines a mapping from V to the field. All right, so first of all, it's linear because if I take C1, oh man, I was going to see, I'm sorry guys, I meant to white that out. Oh well, I've whited other things out, but oh man. So of course this by definition is that, right? But then T is linear, so I can break it apart, pull out the constant, and then lo and behold, I have C times alpha Y of x1 plus alpha Y of x2. Therefore, alpha sub Y is in fact a linear transformation from the vector space to the field. All right, so now I have a linear functional. I have a linear mapping from the vector space to the field, so I can apply theorem 6.8 to select a y prime in V for which alpha sub Y of x is equal to x with y prime. Because remember, the previous theorem said that any linear functional can be realized as the inner product with a specific vector, which we could call the sharp of y if you like. Well, I mean, in my sharp notation, the sharp of alpha sub y is equal to y prime in my notation. But with that construction, we then have that this is equal to T of xy, right? But that's also equal to x y prime for some unique y prime. And that suggests then, you guys stay here, Benjamin. You can't just leave. I don't know where your brother is, but he's got to come and get you. I told him, I don't know what to tell you, Benjamin. I told him to come pick you up here. But there he is. See you later. He's out of energy. He just got done harassing differential equations for like 30 minutes. So anyway, sorry, didn't give you guys the treatment. But if you were on your phone right now, he would tell you to stop, and then he would threaten to shoot you with his Nerf gun. That was what he offered in the last class. Anyway, so the point is that, look, the y prime is unique. So basically that allows us to assign a single valued map from y to y prime. That defines what that's how we're going to define T star. T star of y is equal to y prime, like that. So you see my dissatisfaction of that as a definition, because it's so buried in this, it's buried knee deep in this construction, you know? It's not a very practical definition for the adjoint, but anyway. But it is true though, with this setup, that T of x with y is the inner product of x with T star y, yay. That's the condition that we needed. Now it remains to show that T star so defined, I mean it's a function, great, using the theorem and the construction here, but is it linear and is it unique? Well, linearity is easy enough to check, because if we have y1 and y2 and v and a constant, if we take x with T star, this, well, then by construction of T star, that's equal to T of x with that. But then by sesquilinearity of the inner product, I can pull out C conjugate here and break up the addition, and then I can move the T's back to the other side using the definition of the adjoint once more. And I'm using the property of T star, I should say. And that gives me this, which then proves that, in fact, since that holds for all x, that gives me the linearity of the T star that we do so yearn for. Uniqueness, new for today. I didn't have uniqueness last time, but here's uniqueness. Suppose you have another mapping U such that T of x with y is x with u of y, right? Then that would mean that you have x with T star y is equal to x with u of y for all x. But that would then imply that T star y is equal to U star y for all y, which then would of course imply that T star is equal to U. Therefore, the T star constructed in this way is unique. In other words, if you have a linear transformation which satisfies the identity x, T of x comma y is equal to the inner product of x with T star y, that uniquely defines T star. It's what we're learning from this proof. Right? So basically we're defining T star by its property is a way to say it. Now this we did this lemma last time, yay, right? We did exactly this argument last time. So if you have x with ty, that's also equal to T star x with y, assuming the adjoint exists. I'm in the finite dimensional context here. Warning, when you have an infinite dimensional vector space, it may or may not be the case that the adjoint exists. There's an exercise number 24 in section 6.3 which illustrates this. There you have an infinite dimensional vector space, and what you would want to be the adjoint just can't work. All right. Now, this takes us back to last class. If we have a finite dimensional inner product space with beta and orthonormal basis, then the matrix of the adjoint is the Hermitian conjugate of the matrix for the map. And I like the notation the book uses. It's cleaner than what I did last time, so I'm going to show you. So we'll let A equal to the matrix of T with respect to beta. Let B be the matrix of T adjoint with respect to beta. All right. Then let beta be an orthonormal basis. Well, then, as we discussed a couple days ago, the components of the transformation with respect to the orthonormal basis are simply given by evaluation of the jth basis member, taking the inner product with the ith basis member, right? This is the ith component of that. It gives me that ith component of the column of the coordinate vector of T star Vj. Anyway, then I move it over here. Notice the star is gone. Then I move it back. Notice the conjugate. But this is exactly the matrix of T, but the jith component, because you notice the flippity-floppity of the indices. The j goes first, the I goes second. That's the way this works. All right, we sorted through this, and there you go. That proves that it proves theorem 6.10. Now, similarly, if you have a matrix, the left multiplication by the Hermitian conjugate, the Hermitian adjoint of the matrix is the adjoint of left multiplication by A. So the stars are aligned, I guess. So a standard basis is orthonormal. We prove that, yeah? What? Oh no. Oh no. Well, there's nothing I can do, sadly. Well, I don't know what else I can do. I'm teaching. Bye. I have forgotten my parking decal on the car, and now they're flipping out. All right, anyway. We've got a hang tag. It goes back and forth between two cars. So usually the looptas will call. They usually will at least text you before they're doing anything about it. Anyway, I'm going to go on. So, all right, so the, goodness gracious, it's the worst. Where was I? That was very unhelpful. So left multiplication by A with respect to the standard matrix, the standard basis is just A again, like that is the matrix of L sub A. And likewise, the matrix of left multiplication by the Hermitian adjoint of A is, well, exactly that. All right, again. And so we just proved that the matrix of the adjoint is the adjoint of the matrix of the transformation, and so that implies the result. All right. Nothing much to see here, but nevertheless useful. All right. So next up, this theorem's a little cagey in the sense that it has it doesn't assume finite dimensionality, right? So like if the adjoint can exist in infinite dimensions, it just doesn't have to. All right. Like my proof earlier today that proved that the adjoint exists was based on some finite dimensionality. But if you just know that the adjoint exists, then you can prove that if the adjoint of T and the adjoint of U both exist, then you can prove that the sum, scalar multiple, composition, and the double adjoint, if you will. Well, I think what I should say here is T star star exists. That's a typo. Okay. And okay, so like the proof of all of these is pretty straightforward. Like let's look at one. So like for additivity, if I look at T plus U of X with Y, well that's this. Oh, something else entirely. All right. I wonder what it was like to live in a world without cell phones. That must have been nice. Anyway, hey, I was in that world up until about like college. Anyway, so this is just the definition of the sum, right? And then additivity in the first component. Now right here, going from here to here, I'm using the existence of the adjoint for T and the adjoint for U. But then properties inner product, and then you can identify, oh, okay, so this map satisfies the necessary condition to make it the adjoint. And how do we define the adjoint of the sum? Well, it's the sum of the adjoints. Yay, that's the proof, right? And the proof for C, which is not in the textbook, I think this is like an exercise maybe, but look, it's just as easy. So like this, by definition, is that, right? But then since T adjoint exists, this is equal to U of X with the adjoint acting on Y, which then, since the adjoint of U exists, this is the adjoint of U acting on that with Y, which, by the way, is U star T star acting on Y. And that's why when you take the adjoint, it sock shoes. You can get that sock shoes pattern again, right? So the adjoint of a product is the product of the adjoints, but in reverse order. All of these things also hold for matrices, all right? So that brings us to section 6.4. And at this point, I'm going to start writing stuff out again. I think I can do that. Let me put this away. Sorry, but I wanted to show you those arguments, but I don't think they're sufficiently complicated that you really need to see me work them slowly. Like, they're pretty elementary arguments, but there's also just something in there I get hung up on in terms of the way that the adjoint is constructed in the book. It just weirds me out. Now, if you go back to last class, I've already showed you two different sort of attacks, if you will, on how to calculate the adjoint. The one is to, basically find the matrix, and then just calculate the Hermitian adjoint of the matrix, and then work your way back to the formula. That's one way. That's a fine way. The other way is just to try to directly use the inner product on the formula for the defines the map, and just see if you can't see what formula you need in order to satisfy the adjoint condition. Right? The adjoint condition is what do you think I mean by the adjoint condition? Can you guys tell me? What's the adjoint condition for T? T of X comma Y is equal to what?
X comma T adjoint of Y.
Very good. That is the adjoint condition. So if you can find a formula which satisfies that for your potential T star, you got it. Because that's all that we needed, actually. If you examine the proofs, once you have that formula in a finite dimensional context, everything else falls into place. And my apologies, but I don't really have too much to say about the infinite in here except that you can get into trouble. Okay, so let me continue here. Lemma. Suppose we have T is a linear transformation on V where the dimension of V is equal to n, which is less than infinity. That's just a really obtuse way of saying it's finite dimensional. All right. Then if T has an eigenvector, then so does the adjoint of T. All right. So let's work through this. So I start by saying, suppose there exists x not equal to 0 such that, t of x is equal to lambda x for some lambda in the field, right? That is the t minus lambda times x is equal to 0, right? Okay, let the y be an element of V. And if we look at the inner product, well, first of all, 0, right, is the inner product of 0 with y. But what I'm going to do is I'm going to trade that first 0 for, I'm going to trade this one for that one. Why would I do that? Because I'm trying to gain information about the adjoint, right? And so that all happens, inside the inner product. But by the theorems that I just, talked about with you guys, the adjoint, let me just do it here. So that's x with t minus lambda adjoint, right? Now, t minus lambda is just a shorthand for what? Lambda times the identity, right? And so that is what? That's x with t adjoint minus lambda conjugate, actually, acting on y. Because when you take the adjoint of this, right, that's t star minus lambda conjugate I star. Because when we take the adjoint, the constant gets complex conjugated. And, well, I star is just I again, right? So this is just, which I write that as an abbreviation for. So what's this all mean? Hence, x is, perpendicular to the range of t star minus lambda bar, right? Because its inner product is 0. Notice that t star minus lambda bar acting on y is an arbitrary element of the range. I made no particular restriction on y whatsoever, right? So that's an arbitrary thing in the range, so my claim is legitimate. But what did we know about, what's the deal with this? You know, V is the range of T star minus lambda bar, direct sum, the perp of that, right? And I've just shown you that x is in here, and 0 is not equal to x, right? Consequently, thus, the range of T star minus lambda bar is not equal to the vector space, right? Which then implies that the kernel of T star minus lambda bar is not equal to the 0 subspace by the rank nullity theorem. Because we didn't know the dimension of the range plus the dimension of the kernel, you know, must be the dimension of V. So it follows then that the kernel of T star minus lambda bar is not equal to 0. What does that mean, though? That's just a fancy way of saying, so there exists, you know, like Z not equal to 0 such that what? T star of Z is equal to lambda bar Z, right? Which is to say that the adjoint has an eigenvector. Actually, we get to say a little bit more. Not only does the adjoint have an eigenvector, it has an eigenvector with eigenvalue, the complex conjugate of lambda, right? All right. So, theorem 6.14 is known as Schur's theorem. It says that if you have T, a linear transformation on V, where V is finite dimensional inner product space over F. Then if, you know, P sub T of X, which is the determinant of X minus T, let's say, splits, then there exists orthonormal basis gamma for V such that the matrix of T with respect to this basis is upper triangular. You can look at the text on page 367. The proof for Schur's theorem is honestly a little bit technical, and we only kind of use this as a means for another theorem I'm not actually going to show all the details of. But it is good for you to know what this theorem means, because this is something people know and who've had linear algebra. Like, this is a theorem that's usually discussed. So consider it discussed. All right, so now, what's our goal here? Ultimately, our goal is to find an orthonormal eigenbasis for T. That's really what we want. Like, our ultimate goal in here in this story arc of the course is we wish to find orthonormal eigenbasis for T. And what would that mean? So remember, the problem of finding an eigenbasis is the problem of diagonalizing, right? If you can find an eigenbasis for your transformation, you've diagonalized it. Yeah? And if you can't, well then that brings us kicking and screaming into the Jordan form discussion, right? But if this is the case, and if beta is, that eigenbasis, then T beta beta looks like what? Well, it's a diagonal matrix, right? And so what's the matrix of the adjoint of T in this context with respect to the beta basis? Using the theorem we just proved at the start of class, right? The matrix of the adjoint is the adjoint of the matrix. What's the adjoint, Hermitian adjoint of a diagonal matrix? Transpose conjugate, right? What happens to transposing a diagonal matrix? Well, nothing. Conjugate will conjugate. So d1 bar, d2 bar, dn bar, right? Whoa, hold the phone here. What's that mean? What's the story here? If we can diagonalize T with respect to an orthonormal basis, then we can also, notice the orthonormality is important. We didn't get that theorem about the matrix of the adjoint being the adjoint of the matrix assumed orthonormality of the basis. So that's mission critical. Beta has to be an orthonormal basis. But if beta is an orthonormal basis, then notice that the adjoint is also diagonalized. They're simultaneously diagonalized. What's that mean? What did we prove on the last part of the last problem, the mission that you guys did, that I still need to grade and get back to you? We do have a test coming up, yeah? TikTok. I better get that homework back to you on Friday, hopefully. So we proved that they're simultaneously diagonalized if and only if, given two diagonalizable transformations, right? They're simultaneously diagonalized if and only if what? What's that?
Similar?
No. They have to commute. Remember, if u and t commute, if ut is equal to tu, that implies that they're simultaneously diagonalized, assuming that they're separately diagonalizable. Commutativity is a sufficient condition to give you simultaneous diagonalization. That was, without a doubt, the hardest part in your last homework. Like, significantly harder than anything else on that. But, so what that means then is that this implies that t star is equal to t star t, all right? That's what that means. And in part because of this, we define definition that, as usual, V with the inner product, B inner product space, and T a linear transformation on that, then we say T is normal, right, if T star is equal to T star T. Likewise, a complex n by n matrix is normal if A star is equal to A star A. All right? So can you guys tell me some examples of normal matrices? Let me show you one that's not obvious. Here's one. If I do cosine theta minus sine theta, cosine theta, it turns out that that's actually a normal matrix. Because if you calculate A transpose, you get the identity matrix, and guess what? That's also equal to A transpose times A. And here A transpose is equal to A star because A conjugate is equal to A in the real case. So that's one source of examples, matrices like that. All right? What else? Can you guys tell me? Easy picking here. What's another example of a normal matrix? How about this? What if A transpose is equal to A? Then I believe you can show that that's normal. And also, if you have A transpose, now I might need A is real. I'll have to think more about that. I don't want to think too much about it today, but I might need A is real there to get that to, I mean, certainly if it's real, it's true, right? Because if it's real, then A times A adjoint is equal to A times plus or minus A transpose, right? Which is plus or minus A times A transpose, which I think is, equal to A adjoint times A, if I'm doing this right. Oh, I'm sorry, I can't think. Let me stop. I should just leave that as like an exercise for you guys. Let me not. My brain is not working at the moment. I'm only envisioning people towing my car at the moment. It's completely. Let's see here. Okay, so this is what we mean by normal. A transformation is normal if T times the adjoint is the adjoint times. If a transformation is normal if it commutes with its adjoint. All right? Transformation is normal if it commutes with its adjoint. So again, the question I'm trying to ask and answer today is, when is it that when we have a linear transformation on a finite dimensional inner product space, when can it be diagonalized, actually? Right? When can it be diagonalized with respect to an orthonormal basis? When can it be orthonormally diagonalized? Because that's really the best we can hope for. Come on. Is it come back? All right, came back. All right. So we just did this, and we did that. I mean, that example is straight from the textbook, so it's probably true. But I can't remember the context of the example, is why I'm a little bit wishy-washy, all right? But here's the next theorem. And so the next theorem here, 6.15, it's if you had a normal transformation, it preserves the length of vectors under the adjoint. Like length of t of x and the length of t star x. T star acting on x is the same. T minus ci is normal for any constant. If you have something that's basically this says if you've got an eigenvector of t, then guess what? That's also an eigenvector of the adjoint of t. This is stronger than the lemma we proved. You notice that the z that I came to, it had no particular connection to the x I started with. This is a stronger result. It's saying that not only if you have an eigenvector with eigenvalue lambda, you have an eigenvector with eigenvalue lambda bar, but guess what? Same vector. That's a much stronger result than we had in my lemma earlier. And then finally, if lambda 1 is not equal to lambda 2, then the corresponding eigenvectors x1 and x2 are in fact perpendicular. Now, so the proof that the length is preserved is pretty simple, like the usual thing. Length squared, inner product of vector with itself. Use the property defining the adjoint, right? The adjoint property, yay. Commute t and t star, all right. And then move t back over there. Recognize that you're looking at the length squared of t star x, and you're done. So that's not bad. Not bad. And here's the proof of b. This is not in the note, not in the book. Like the book doesn't have this one, but I worked this one out for you guys. So like if we have t star t is equal to t star, we use properties of star. So like the adjoint of this is t star minus c bar I, because I star is equal to I, all right? And multiply that out. And do the same for the opposite order and meet in the middle. They're equal because those are equal because t is normal. We assume t is normal. Therefore, t minus ci is normal. Now, the proofs of c and d are given on page 368 and 369 of the text. I am sorry, I just ran out of time. They are good proofs. Like those are decent, like test questions even. Like if I stated them properly in their full context, they'd make decent like test questions. Actually, those. I'm pretty sure. If you look at them later and you decide that you think I'm crazy to say that, well, let me know. Now this one here, theorem 6.16. Let V be a finite dimensional complex inner product space. T a linear transformation. Look at this. This is like the main event right here. One of two main events. It says T is normal if and only if there exists an orthonormal eigenbasis for T, of eigenvectors for T. So the other direction I just covered up. We argued the reverse direction already because we showed that if that was the case, then that means T and T star are simultaneously diagonalizable, which means that T star T is equal to T star, which is to say that T is normal. So we've already proved the converse direction of this. And the forward direction is technical, and it uses Schur's theorem. It's not actually that easy. It would take me a half-hour class to prove this theorem. But to whom much is given, much is required. So I do not require of you the proof of this theorem. But I would like you to know it and be able to use it. Yeah? So understanding the statement of the theorem is really where I'm more interested in for us here. And then the next thing is the definition of self-adjoint. So a matrix is self-adjoint means that T is equal to its adjoint. T is equal to T star. And likewise, a matrix is self-adjoint if A is equal to A star. They can also be called a Hermitian matrix or operator, right? And in the context of a real vector space, you notice that the condition of Hermitian just reduces to this condition of symmetric. So self-adjoint is symmetric in the real case, right? A symmetric matrix, or you could talk about a symmetric operator even. Now, so here's the a lemma, which is kind of a checkpoint on the way to the main result, which is down here. But if we have a self-adjoint operator in a finite dimensional product space, then things that are pretty awesome is, one thing is every eigenvalue is real. That's wonderful. That means that you have enough eigenvalues. There's no complex eigenvalues. That's what it's saying. And if V is a real inner product space, then the characteristic polynomial splits. Which is to say that you have, that's just another way of saying you have an eigenbasis. If the characteristic polynomial, well, it's not saying that, but this theorem is. We don't really care so much about the lemma as we care about the theorem. So the theorem says if we have a linear transformation on a real inner product space, then T is self-adjoint if and only if there exists an orthonormal eigenbasis for T. And that's kind of it. Like that's the central result here. Self-adjoint if and only if there is an orthonormal eigenbasis. Now, so next up, we want to think about unitary operators. A unitary operator is one which preserves length, basically, in this story. In the complex case, we call it unitary. In the real case, we call it orthogonal. All right, and so the basic theorem about unitary operators is given here, theorem 6.18, and that says that the following are equivalent. T star T equals to I, T times T star equal to I. The inner product of T of X of T of Y is equal to that. If beta is an orthonormal basis, then the image is orthonormal. If you have an orthonormal basis, well, there exists an orthonormal basis such that the image is an orthonormal basis. I've probably not done justice to the grammar here. If you look in the book, maybe you can see, maybe I've like missed a word or something. It feels like the same thing to me, but anyway, I always have this feeling about that. And then of course the length is preserved under T. That is your problem 50. Don't be afraid of this problem. It's actually not much more difficult than the proofs we just looked through. You can do this one. It's not bad. Don't be scared of it, despite its many parts. And that brings us to the main event, but this time written for matrices, and a little bit more, kind of like what you were getting at, Jonathan, I think, earlier. A is normal if and only if it's similar to a diagonal matrix for some unitary matrix U. So not only is it diagonalizable, it's unitarily diagonalizable. And the way you make a unitary matrix actually is you take an orthonormal basis and just concatenate them. Like if we're talking about Cn, if you just stack orthonormal complex n vectors together into a matrix, if my memory serves me correctly, that makes a unitary matrix. Just like in the real case, if you take a real orthonormal basis for Rn and you stack those together, you can glue them together and make an n by n matrix like that, that gives you a orthogonal matrix, right? So like every orthogonal matrix corresponds uniquely to a orthonormal basis and vice versa. But a matrix is symmetric if and only if it's similar to a diagonal matrix. And not just similar, but it's orthonormally similar, orthogonally similar. In other words, the similarity transformation happens with respect to an orthogonal matrix. An orthogonal matrix is simply one that has R transpose R equals to the identity. Unitary means that U dagger U equals to the identity. But we'll talk more about unitary and orthogonal like that. Next class, I'm going to spend just talking about unitary versus orthogonal, what that all means and how that works. But these are the main theorems that, this is the reason we're even talking about the adjoint and all this, is to understand these theorems basically. So my apology that I haven't managed to create enough class time on this topic to give you the full proof of the central theorem, but again, then I won't test you on it either, so yay. I will test you hopefully on the statement of the theorem, so I want you to understand what they're saying. And I hope the homework helps you with that too, but that's all I got for today, I think. So.